Good morning or good afternoon, everybody. Welcome back to lecture number
23.
23.
Yes, we are on week 8.
22, how can we do?
No, we count even the one we skipped, we count.
On Sunday it was 22.
Oh, Sunday 20. Okay, this is 20. So we are all in week 8, صح? So last time we talked about voltage over frequency control. You remember that? And what was the key benefit? Key benefit is we keep the flux constant until what? Until the rated voltage. Anything beyond rated voltage is a violation. You cannot apply higher voltage on your induction motor. Think if you apply 300 volt on your 220 vacuum cleaner, for example. What will happen to it? It will burn. Back in a few years ago, you remember we used to burn devices because we plug 220 on a 110 device on a 220 plug. So you cannot exceed rated voltage because you have so much current. V over F, after rated voltage, we enter into, what's the name of that region?
Flux weakening.
Flux weakening. So this is most likely a target question. Okay, this is most likely a target question in the test. And please, I don't want to see in exam 2, which is going to be in
April 5.
April 5. Any objection? Any objection? Okay. So, in April 5, we will have the formula sheet. Where's the formula sheet? So make sure to include labels to tell this is a phase quantity or line to line. Okay? So we don't want to repeat the same story that happened in major. Also, you are allowed to write text. Okay? For example, different names, complicated names, anything you want. And in exam 2, you will have 2 sides. Side 1 and side 2. Or 2 pages. I'll print 2 documents. I don't care. Okay? And then the final exam, it will be 3 pages. Okay? So what happened last time? Last time we talked about the V over F control. And in the V over F control, we mainly targeted, we talked about the poles, but this is useless. So in the pole control, if you reduce number of poles from 6 to 2, you reduce your starting torque. But the slip will be the same, because the slip is relative to speed. And what will happen? So S max will be the same. We will have, if we change number of poles, we will reduce maximum torque and the starting torque and the torque in general. So if you increase number of poles, what will happen? Your torque becomes lower. Okay? And how do we achieve that? By changing the coils. For example, between 6 and 12 pole, this is one example, is if you connect 2 coils in parallel, if you split them in series, you will achieve double poles. And then what will happen to the speed? Doubled or halved. The speed will be halved. Okay? Then we talked about frequency control, and if we do not do anything with the voltage, the more we increase the frequency, the lower the torque becomes. And this is useless, because what if I want to run at these speeds? Yeah, okay, I can skip this very high speed. So that's why we come up with V over F to push some of those curves up until we reach the rated voltage. What's the limit on V over F?
Rated voltage.
This is one of the questions in the MCQ. Okay? Keep in mind that T max reduced as we increase F. Also starting torque is reduced. To increase the frequency, starting torque, what will happen to it? It will reduce drop. And the peak torque drops. Okay? At low frequencies, what's the problem? Saturation. We will saturate our cores. And what is the advantage of frequency control? wide range of speed. So this is حفظ, okay? It's important. Last question in the test. And I told you, what's the most common type of inverter for frequency control? Back-to-back converter. These two methods are old. Back-to-back converter is so powerful that we can even use it for V over F control. So you need to know what is variable voltage, variable frequency drive, and what else I told you? Variable speed inverter, variable speed drive, all those 4 names for the same technology. And what is the advantage? You keep Tmax constant, you can increase your starting torque. Why? Because in frequency control, starting torque will reduce. And this is a problem. Why it's a problem? Because if you have a constant load, certain frequencies, high frequencies, will not be able to drive the load initially. That's the problem. If you have a starting torque, say maybe 180, this frequency, and that frequency cannot drive the load. That's the problem. So what's the solution? V over F. Okay? V over F. And as you can see with V over F, if you look at the torque, it's fixed constant as long as V rated is not achieved. If we achieve V rated, we have to drop because we enter the flux weakening curve. What will happen to the current if we increase the frequency for the same speed? For the same speed, we will have
Constant.
no, not constant. So this is speed versus current. So for that frequency, for the same speed, you get lower current. This frequency, yeah, it's the same for the same speed, yeah. Well, they have different speeds, but this has to do with the starting current. We will see it later. This curve is not important, okay? It's somehow misleading. But the idea about it is if you change the frequency, you're already changing the speed, and the currents are confined. For the faster speed, you can have the same current by just changing V over F. The idea here is starting current is constant for the same speed. Well, they don't have the same speed. Okay? What is the limit for variable voltage, variable frequency? We cannot exceed rated value. And what is this controller? 380. Next class. What's this controller?
PID.
This is P. What is this controller? I. This is what I want you to know. PI controller. P controller gives you voltage. I controller gives you firing angle, alpha. Okay? And here you have sensors from the AC or the DC?
The DC.
From the DC side, from this capacitor on the DC. Remember, here we have rectifier, here we have source. So we get the data from here. So let's look at this example. At a 480 volt 2-pole machine, so this is line to line or phase. If he didn't tell like in the test, it's a phase. It's a line to line. If he said like in the test, where we had the confusion, in the test what we had is, we had phase quantity because your formula, where's the formula sheet guys? So the formula sheet was written in terms of phase quantity. And the example was written. So this is line to line or phase? Line to line, because there is no 3. Okay? So in the formula sheet, in the exam, make sure you to include the right formula. Or write down, this V is line to line. Or write down, this V is phase. Okay? And here what do we have? We have reactance of 4, resistance of 0.2. Okay? And another R, this is R1, R2 is 0.3. And this is X1. Okay? The motor is driving constant torque load, so we operate at constant torque load of 60 Newton meter at speed 3500. What is this for 3500? Is it synchronous speed or full load speed?
Full load speed.
This is a full load speed. What is the synchronous speed?
120 times.
No, it's 360. 3600 RPM for 2-pole machine. So what's the slip? What's the slip?
360 times
100 على 1100 على 3600. Okay? So your slip is 2.7, 2.8. Okay? Then what is happening? What will happen? Next is assume that the torque included is in the rotational computation. What does this statement mean? This statement means the developed torque equals to the air gap torque. Do you remember in the air gap torque? The electrical torque that crosses the air gap. Then we have developed torque on the shaft. So this means we ignore the friction. Okay? Because if you remember, T gap equal T shaft plus T friction. في عزم للاحتكاك. عزم الاحتكاك وعزم الشافت هو العزم اللي ينتج من المجال المغناطيسي. Clear?
yes.
Okay? So who's late? We have 2 late. Please mark yourself as late. Okay? Now what else do we have? Write L next to your name. Compute the maximum frequency of the supply voltage that would not result in installing the motor. So what is the idea behind this question? Find the maximum frequency of the supply voltage that would not result in installing the motor. So we have to pick the maximum torque. So what is the maximum torque equation? Is V squared over 2 omega S R1 plus R1 squared plus X equivalent squared. This is one of the old equations. This is 360 equation. Okay, this is from 360. So now we have V is line to line. Maximum torque due to 3-phase based on the values of R1 and R equivalent. He is making an assumption here. Assume R1 squared is much smaller than X equivalent squared. So this leaves us with X equivalent here. The maximum torque can be approximated. Remember that V1 is V line over square root of 3. This is V1 in the formula sheet that you developed before. V is line to line. This is phase. It's called V1 or VF. Same names. V alone is line to line. So this is the torque equation if we ignore the R1s. Okay? If we ignore the R1. This is written in terms of phase. This is written in terms of line to line. Okay? So what he's doing here is he is asked to calculate the frequency. So what is happening here? What is happening is, what is omega S? It's 2 pi over 60 ns, right?
Yes.
What is X equivalent? It is J 2 pi F, or we call it omega electrical. This is electrical. This is mechanical. Because impedance is electrical. Speed is mechanical. And this is L. So what he is doing here is he is multiplying by F, dividing by 60. Why? Trick. Because omega S is calculated at 60 using this formula 2 pi. What is NS? 120 60 over 2. And what is X equivalent? Is calculated at 60. So he divide by 60 and he multiplied by the needed frequency. This is a trick in machines. F over 60 trick. What's the F over 60 trick? And instead of recalculating X equivalent, recalculating n omega S, you just multiply by F and divide by 60. So here we had frequency squared because we have two quantities that rely on frequency. Can we all solve this equation?
Yes.
Can we solve it all?
Yes, yes.
If we solve it all, this is easy, right? It's F squared equal 480 squared over 60 times 2 times 2 pi over 60, 3600 over 60 times 4 over 60. This is math 101. Okay? But do you understand why we have F over 60 now? Is it clear? Because X equivalent is, this might be a question in the test. Why we have the F over 60? Because X equivalent is calculated at 60 Hertz, omega S is calculated at 60 Hertz. So we negate the effect by dividing by 60 here, by dividing by 60 here and multiplied by F. And it turned out that the frequency is 67 Hertz. What is this frequency? Is the frequency, maximum frequency of the supply voltage that would not result in stalling the motor. It means it is the maximum frequency in this control. So what is, it's 180, right? Well, this curve, let's pretend this is 180. Okay, let's pretend. So this is 180. So it is the frequency that its peak doesn't exceed the load, which is this frequency. Okay? Clear? So this is the load, pretend this is 180. These are all the frequencies. Maybe the 60 Hertz is this one. This is the 67. Or no, 67 is here. Exactly in the right here. Okay? But because of the approximations, it's a little bit lower. Clear? Do you understand this question now?
Yes.
Please, this question is very important and interesting. Now, the other question is calculate the motor current at 60 and the maximum frequency, which is 67. This is easy. Go back to 360. Calculate starting current at 60 Hertz. Calculate starting current at 67 Hertz. So what are the equations? This is the equation for 60 Hertz. If you remember, this is the equation from 360. V over square root of R1 plus R2 prime over S square plus X equivalent square. He's using the equivalent circuit. Okay? He's using the equivalent circuit of something like that.
Circuit 1 or 2?
No, he's putting R1, this is R1 plus R2 prime.
Yes.
And he's putting here R2 prime over S. And this is X, no, X equivalent here. No, X equivalent is here. So that's the current. X equivalent is here. Other line, this is Xm. So this is the starting current. It's the current that goes here. Clear? It's this current. It's using circuit 2 if you go back to my 360 videos. So what is the slip we already calculated? You have to plug the slip here. Don't forget the slip. It means you also have to calculate the slip at 67 Hertz. You have to calculate the slip at 67 Hertz. So this is 360, 480 over square root of 3. Here, is he using phase or line to line?
Phase. Line time.
Line, he's using phase. Here, he's using F as V as 480. So this is a mistake, right? So instead, this should be
480 over square root of 3.
Square root of 3.
F1.
Yeah.
Okay? Calculate this to F1. U2. Calculate this, correct this to F1. This is a mistake, صح ولا لا? It's 480 over square root of 3. Clearly this is V1, not V, or V phase. So if you calculate the current, it's what? 23.62 amp. Any question how to calculate the starting current? Yes.
Shouldn't be both of the currents, the starting current, يعني رايح للإكس
XM.
XM.
No,
Also
the
the-
XM is very, very small.
So we ignore it.
Yes, ignore it. But the starting current, it's actually, and from the circuit's point of view, it's this current. Okay?
Because we had the
We use approximation. If you use circuit, yeah.
in the previous example.
Is
we
XM
found-
given? Is XM given? If it's not given, you can assume it's very high. So this is very high. It's not given. Okay? Just ignore it. Okay? Go back to the 67 Hertz. What do you need to do? You need to readjust your X equivalent by multiplying it by 67.7 over 60 times 4. This is the new quantity, 4.51 ohms. You also need to calculate the new slip. Here he calculated slip max. Okay?
It's required, I think, of the question.
Yeah, that's slip max. But why he calculated the slip max? Why not just the slip?
Maybe required from the question.
No. The question is, Oh, okay, because it's the maximum frequency that gives the maximum torque, so it gives the maximum slip. Because this thing, maximum frequency gives maximum torque, gives maximum slip, SM. So he calculated SM. If you do this calculation, NS minus N over NS for 67 Hz, you should get the same number. But this is slip max, okay? Use slip max because the torque at this frequency is the maximum. And he plugged the two numbers and it's 42.5, okay? And the motor speed is 3792. And what do you notice here? 42.5 starting current versus 423.62. So this is not the starting current, this is the rated current. This is the maximum current. Remember, you're driving your motor to its torque, for frequency 60 Hz, you're operated at rated. So you're operating at, what is the, let me explain it from Kerr's point of view. From Kerr's point of view, where is your torque? 180, right? صح? For the 60 Hz curve, you're operating at this slip. So this is 60 Hz. For the 67 frequency, you're operating at no, my bad. It's wrong here. For the 67 Hz, you're operating at this curve. Clearly? You see it now? This is the 67. I'm exaggerating. But the slip, this is, or not really here. And we can say it's here. So you see the two different points. So here we're operating at the peak, here we're operating at the linear region. You understand this curve? Or should I repeat it? I want one repeat.
One repeat.
Repeat? Let's repeat. Originally, nice machine, how does it look like? For 60 Hz, this is 180. You agree with me?
Yes.
Constant torque. For the 60 Hz machine, we're operating at maybe, no, let's say, okay, this is traditional, صح?
Yes.
You agree? This is traditional. This is at 60 Hz. So we're operating at the linear region. So this is your point of operation. This is your slip rated. Okay? Keep in mind we're going to have, this is omega rated. What will happen if you increase the frequency? Your omega should shift to the right or to the left?
Right.
To the right, because we have faster speed. At 67 Hz, which is now the blue, we will begin here. Let's say, how can I make it? Let's say we begin here a little bit. No, let's say we begin lower than that. This is too high. This is TL. Do you agree with me?
Okay.
We're operating at this omega rated. Do you agree with me that 60 Hz? Does this sound look better? Okay? This is 60 Hz. Do you agree with me?
Okay.
Let's say we operate I'm making it too low. معلش. Should make it higher. If you increase the frequency, how does it look like?
Top.
Lower starting torque,
Yes.
the peak will be later, and it will be less.
Yes.
Okay? So this is at 67. Okay? Now, the load, in this case, we make this a little bit, yeah. Let's start smaller, that's okay. الفكرة إنه this is T load. Here's the intersection, here's the intersection. I'm making the peak torque of the second frequency cut exactly at the load line, while in the 60 Hertz, it's in the linear region. So the slip here we have omega 2 max. So I'm increasing my slip for the 67 Hertz, while in the original slip for the 60 Hertz is lower. Looking at the curve, looking at this curve, this is the 180. So this one is the 60. This one is the 67. Clear now?
Yes. Doctor, isn't like overall it's a negative to you operate at 67 because you're operating at maximum while being like not in the stable region.
It is, anything above that it will not be stable.
Yes. So
Okay?
what's the benefit of operating at 67?
So
You get higher speed. No.
you get higher speed, but also you get lower starting current
And lower torque.
and lower torque. Keep in mind what is happening if you run at 60 Hertz. The load would start to spin. But at the lower, if starting torque is less, you have to wait until you exceed the maximum torque and then it will start spinning. Get it? ففي 67 Hertz, the load will not spin until you exceed a certain speed. For the 60 Hertz, the load would spin initially at 0 speed because the starting torque is larger than the load torque. You understand that?
Yes.
الكارثة في these two curves, maybe 70, maybe 80, they will never drive the load.
Because starting is
Because even في الستارتنج torque إذا كان أقل من اللود بيقعد معلم until you reach the maximum. This is class A and B. That's why we need class D and C to start moving from low speed. So the machine would start spin and then it will start spinning there. There will be inertia. Now this is in theory. In real life, you have to run at starting torque. In real life, you have to run at starting torque because you're gonna have so much high current until you drive the machine. You don't want to wait until the max. But this is from machine's perspective, not shaft perspective. You understand what I'm saying? Is it clear?
Yes.
So these two curves will not drive the load. This curve would drive the load, but barely, only in the peak. It may even, if you increase the speed a little bit, it may not be able to drive the load. So here the question was talking about this problem, barely moving the load. That would not result in stalling the motor. The motor would not stop, okay? Because you reach the maximum torque. Calculate the motor current at 60 Hertz, it was 23, at 67 it was 42.5. That's high. For a small increase in frequency, because the maximum torque dropped, that's too high. And what was the last question? The last question was calculate the power delivered to the load at 60 Hertz and at this maximum frequency. So develop torque is developed power is developed torque, which is 60. Sorry, this is not 180, this is 60. Developed torque is 60 times omega, which is 2 pi times rated speed. This is developed, not air gap, not magnetic torque. This is developed torque, which has omega rated to 3500 times 2 pi over 60 times 60, this is 22 kilowatts. At 67 hertz, the speed is 3792. That's the speed. This is how we calculate it. You get the slip, you convert the slip, you calculate NS, which is, this is NS2, the second speed. You get the speed 3792 and you get the power 23. So that's an increase of 8.3%, imperative that the drive system be barely able to handle this load. Okay? So this is your limit. If you drive any frequency above 67, your load will not be driven. Your load will not be driven. But is this a good speed to operate at? No, because it has very high current, it's not stable. With mechanical losses, you may not be able to drive the load. Okay? Now, the question asks you to repeat your calculation using 50 Hertz. What will happen if I reduce from 60 to 50 Hertz? What will happen is I'll have a new synchronous speed, 3000. I'm going to have a new omega S, and we need to calculate the slip. But the problem here, he is not telling you the speed. In example 2, he gave you the speed of 3500 RPM. Now, what is the corresponding speed for the 50 Hertz? You have to calculate it using the torque equation. This is the torque equation. T developed equal Vt square S over omega S R2 prime. Is this line to line or phase?
Line to line.
So this V is correct. Okay? You have to pay attention, please, for the formula sheet. So this is 480 squared times S over omega S, which is 314. It happened to be 314. Times R2 prime, which is 0.3, so the slip is 2.45%. Now, what is the speed at this level? It's 2926. So you get the slip, then you get the speed, if it's not given, through the torque. Through the torque. So you get the torque, then you get the slip 2, and then you get NS2. 2 means the new one, at 50 Hertz. So this is at 50 Hertz. And is it clear?
Yes.
واضح? Is it clear? So you get the torque, you get the slip, you get the new speed, which is 2926.5. The synchronous speed is 3000. That's 19% reduction in speed compared to 3500. Compared to 3500. Then you calculate the starting torque. Again, here use V1. This is phase, not line to line. Okay, I'll try to fix the slides. So this is 68.75.
Is that 60?
What was it? This is at 60 Hertz. What's the starting torque at 50 Hertz? It's 82. So starting torque is higher. Look at the curve. If you increase the frequency, starting torque will be higher and starting current will be higher. So that's why we need to use V over F to keep starting current constant. Yeah, starting current is higher. So this is very bad or huge number, and try to do these calculations yourself, okay? The last example is, let's do V over F and see what will happen. So V over F, it means, and this is V over F demo. It's very easy. At 60 Hertz, what is V? 480, line to line. So what is your V over F? 480 over 60. What's this ratio? 48 تقسيم 6 8. So what is your V over F? 8. You go to the 50 hertz, V over F is 8, which is the new V. Let's call it V new. Let's call it V new over 50 hertz. So what is your V new?
400.
8 times 50, which is 400 voltage line to line. So now I'm not gonna keep it at 480. V over F tells me, okay, so can I operate at higher voltage? No. So now I'm comparing the two ratios. So I'm gonna have a new V over F. Keep in mind, V over F is baked in as V over omega. It's inside. The ratio is inside. That keeps the torque. That keeps the torque alive. That keeps the torque 60. So if you put the new numbers, you get a new slip at 50 hertz. Remember, this is 50 hertz. So your new slip is 3.53. What was your old slip? 2.45. So we have to increase the slip for lower frequency in V over F. We increase the slip for lower frequency for V over F. So what is happening here is you get a speed to be 2894 compared to 29 something. And you do the calculation again with the starting torque at 60 hertz. With the old V over F, it was 68.75. It was here 68.75. You do the same calculation here. Keep in mind, he multiplied by 50 over 60. This is frequency adjustment for X equivalent. If you do the same calculation here, the only change he made is the 480 becomes 400. So it will be 68.5. A smart student would use the old speed, the old current, which is 82.21. He would just multiply it by 400 and divide by 480. That's a quick way to do it. Can we verify? 82.21 times 400 divided by 480. So you should get the same number. Not really. 68.5. It doesn't matter. 67, 68, doesn't matter. Okay, that's another way of doing it. Okay?
Is it legal to do it?
Yes. Because this is not V squared, it's a function of V. If it's function of V squared, yeah. The reason I'm not getting the exact number because he's approximating this number. Yeah, if you use the exact number from answer and multiply by 400 over 480, you should get the exact number. Okay? I don't care if you get 67, 69, 70, I don't care. As long as you are close. Okay? Now, let's talk about the last. So we talked about, let's go back to all the previous techniques. What did we have before? You remember?
One, adding resistance.
We finished, we talked about adding resistance, talked about voltage, talked about poles, talked about frequency, and we talked about V over F. The last one is our most preferred one, is slip energy recovery, if you want to control the rotor side. Now before you control the rotor side, can you do it in a squirrel cage? No. It's only done same for adding resistance, only for wound rotor, where the rotor has some windings. Okay? So your V over F, if you have a squirrel cage, you may use slip energy recovery for wound rotor motors. But most of the industry use V over F because most of the motors are squirrel cage in industry. So if you have a wound rotor, you have to use slip energy recovery. Slip energy recovery is a very interesting concept that I think it adds value to your education. So the idea is very smart and it's very simple. Let me read the text and I will explain it. If the slip power lost in the resistance could be returned to the AC source. So what was the problem with adding resistance? We have I squared are added losses. Can I somehow, instead of connecting real resistors, can I reconnect it to the grid and the effective Thevenin resistance seen from the motor by the source? Can I use it so that I'm not going to have resistors, I'm tapping from a supply what looks like a resistor. This way I can reduce my losses. So the idea here is, if the slip power loss in the resistance could be returned to the AC source, the overall efficiency will be increased. So what is the main benefit from slip energy recovery control?
Increasing the efficiency.
Improve the efficiency. Question the test. This is one of the MCQ. Guaranteed. Guaranteed, يعني 90% I'll bring. If I remember, I'll bring it. Okay? That's what it means. Guaranteed. If I see it and I remember, I'll bring it. The rotor power can be rectified by the diode bridge. Now we use the power electronics. The rectified current is smoothed by this inductor. So what is the purpose of, we call it chuck. What's the purpose of this chuck? Smooth. So this inductor is for smoothing. The output of the rectifier is connected to DC terminal of the inverter. This is inverter, which inverts this DC to the grid back. Sometimes, not all the time, they add a transformer here to ensure you get 60 Hertz and rated voltage. If the inverter does not give you rated voltage, you have to connect it to, so the inverter would give you 60 Hertz but give you V out. If V output is not same as V supply, you have to connect a transformer. If the output of the inverter same as the supply, no need for the transformer. Sometimes you will see transformer. So slip energy recovery is, if you look at as a rotor, you look here, what do you see? You see just impedance. So this impedance is actually lost in the supply, so we're not losing, because we're feeding it again to the source. Clear?
Yes.
So the idea of the slip energy recovery, we're not going to do numerical examples, it's just a concept, is you have to control your firing angle to change the effective impedance seen by the rotor. If you make alpha smaller, your effective resistance is going to be smaller. Let's go back. It's very similar idea to what we had before for the adding resistors. Do you remember here I told you we add inverter to, the more we close the breaker, the more we short circuit. So the more we send firing angle, the less effective resistance seen by the supply. So the idea here is you have a supply, you disconnect, connect. The more you connect, the more you get to see the impedance. Okay? Now the details, how it operates, it's beyond the scope of this course. What you need to know is slip energy recovery is you use power electronics with firing angles to change the effective impedance seen in the source, but that impedance seen in the source, you lose energy in the supply. You don't lose it in the motor itself, and you retrieve it back. So that's energy recovery. It's a very smart technique, but it's only, the downside, it's only for wound rotor. It's not used for squirrel cage. Okay? Now, if you change the alpha 1, alpha 2, alpha 3, you can change the speed, and the torque here is depending on the this actually looks like that. Originally it looks like that. Okay? So your torque is constant. So slip energy recovery, you operate in the linear region. Okay? الخطوط هذه is the linear region of the capability curve of your motors. So if you change the speed, you can shift the energy recovery. Is the camera still running?
Yes.
Okay. So the equation for the initial slip is minus V1 over E2. E2 is here, the voltage here. V1 is the voltage here, times cosine alpha. Alpha is the firing angle, alpha 4, alpha 3, alpha 2, alpha 1. The smaller the alpha, the larger the slip. The larger the slip means slower the machine. Clear? So large alpha, smaller cosine. Smaller cosine, no, larger cosine. No. Smaller alpha, larger cosine, because cosine of 0 is 1. So larger cosine means larger slip. Larger slip means slower speed. So we conclude that alpha 4 is smaller than alpha 3, smaller than alpha 2. Is it small now? Yeah, it's small. Okay? Where this is no load slip. Okay, this is if you don't connect it to the slip. Now, what is the energy recovery? I'll take some time. You recover the copper losses, some of it, not all of it, some of it, you retrieve it back to your inputs. So your energy efficiency for slip energy recovery is P output over P input. So, no, P output over P source. So is P source with slip energy larger or smaller? It's smaller. So you get higher efficiency. Eta for non-slip energy recovery is P output over P supply. Is P supply now without slip energy recovery, is it larger or smaller?
Smaller.
It is
Smaller.
smaller. So your efficiency would be smaller. You divide by a larger number. It will be, P source here is larger. فكر فيها شوي. Slip, this is a nice trick. We will start with this trick. Remind us next lecture. Okay? In summary, the trick here, you minimize your source supply because you're recovering some of the energy. You're minimizing the supply, so if you minimize source, you increase the efficiency. If you maximize, if you make source more, your efficiency is lower. So slip energy would improve the efficiency. Thank you all. Any question?